Good afternoon, everyone. We are back to our video course on silicon and wide bandgap power devices, lecture number 26. I'm Professor Anant Agarwal at OSU, and again with me is my colleague Dr. Arash Salami. And this course was funded by Office of Naval Research. So today we will discuss the superjunction MOSFET, also called as cool MOS. So let us first go and review the MOSFET structure that we have been talking about. So this MOSFET structure has a P-well. Inside the P-well is N plus source, and then you have the N-type drift layer and the N plus substrate. Sometimes there is an N-type buffer layer between the drift region and the N plus substrate. And when we apply the gate voltage of 0 volts, there is no inversion layer here, so there is no current flowing, and in that situation this PN junction here blocks the voltage, right, this one and this one, and the JFET region is fully depleted out, so this entire drift layer supports the voltage. So if we look at this PN junction in the next slide, under the blocking state, that PN junction is reverse biased. The electric field is maximum at the junction of the P with N drift layer, and then the electric field is reduced linearly till it hits the N plus region, and then the electric field rapidly reduces to 0, and same thing on the P base side, the electric field goes to 0. Since the P base is much higher doped than N drift layer, we can generally neglect WP. So the area under this curve gives you the breakdown voltage of this device. So, few observations. So, this junction will break down when this electric field, maximum electric field, reaches the breakdown field of the semiconductor silicon or silicon carbide. And then area under this electric field represents the applied forward voltage on the MOSFET. It actually is the reverse voltage across the PN junction. So the breakdown voltage is decided by essentially this electric field line, because that decides the area under the curve. Now, in order, if we want to increase this breakdown voltage, we have to think of a structure where the electric field doesn't reduce like this. It almost stays constant throughout the drift layer. And we are of course talking about the Y direction of the MOSFET. Then you can see the breakdown voltage will increase if we can keep the electric field constant in the drift region or close enough. So that is the purpose of the superjunction MOSFET, which we will show you in the next slide. So here, this is the superjunction MOSFET, also known as cool MOS, and we have the same P-well, same N plus source, N type drift layer. The difference is in the regular DMOSFET, this region used to be the N-type drift layer. Now we have made it P-type drift region. So, this region is doped as P-type, and then as we will show you, this region can be doped little more heavily, quite a bit more heavily. So, what happens when we apply positive voltage on the drain, the drift region here depletes along this direction in the vertical direction, but also it depletes sideways from the P to N. So, this whole N-type region gets depleted vertically and horizontally. So, there is a two-dimensional charge coupling. So, this allows us to keep the electric field constant in the y direction like we were suggesting in the previous slide, and we can dope this region much more heavily, and we will show you how we can make a device like this. It's pretty common in silicon, but in silicon carbide we have not figured out a good way to make it yet. So, anyway, you can read something about this in the original publication in 1999 from Leo Lawrence of Infineon. This is a structure is available as a MOSFET in silicon up to about 900 volts. So, here is that structure again, and one thing that we need to understand is that this is only half the cell, the other half is on this side. So, Wn is the width of the N-type drift layer, and Wp is the width of the P-type layer on this side, and then this is just half the cell, and P-type is doped with Na, and the N side is doped with Nd. Here is the substrate, and here is that buffer layer we had mentioned. So, one thing that is useful is that when we apply reverse bias, we want to deplete both P and N in the x direction first of all. So, that tells us that the charge times the width of the N side should be equal to the charge on the P side. So, we can say that Nd times Wn should be equal to Na times Wp, and at some small voltage on the drain, this both P-type pillars and N-type pillars would be fully depleted. And when they are fully depleted, then any additional drain voltage we apply will be dropped across the y direction, and the electric field in the y direction will keep on increasing up to a maximum value when the semiconductor breaks down. So, this allows us to make these pillar widths very narrow and dope them very heavily, so that the on resistance, which is the resistance of the N-type pillar, is much lower than the planar DMOSFET structure. So, let us see how that happens. So, we take a case of a 200 volt structure from Professor Baliga's lecture notes and books, and you can see that this is a P-type pillar, this is the N-type pillar, and both are doped at 2 times 10 to the 16, and N-type drift region, half of it is 0.75 micron, but the full N would be 1.5 up to this point. Similarly, P is 0.75 micron, but for the full cell it would be 1.5 micron. So, now this is equipotential contours at 20 volts on the drain here. So, you can see that both P and N pillars are depleting sideways, and once they are fully depleted, then additional drain voltage goes across the Y direction. So, these are the contours at 200 volts. You can see that the Y field is very constant because the spacing between the contours is almost constant, and when that Y field reaches the breakdown field of the semiconductor, this device will reach its blocking voltage. So, in X direction we fully depleted at small drain voltages, and then in Y direction we have a high electric field that drops a lot of blocking voltage. So, basically we have been able to essentially get something similar to this constant electric field in the Y direction which we had suggested. All right. So, now we have a 600 volt again from Professor Baliga's lecture notes, and you can see at 50 volts it's almost fully depleted, but not quite, and here is at 100 volts. You can see that the field in the Y direction is building up, and the electric field seems to be higher in the bottom than on this side because the potential contour lines are closer together at the bottom. And here is at 600 volts, you can see that potential lines of contour are very horizontal, and that means the vertical field is almost constant, except it rises a little bit towards the substrate because you can see the lines a little closer. But nevertheless, the principle is you deplete P and N type pillars at low drain voltages, and then any additional voltage goes across the Y direction where the field in the Y direction is almost constant. Pretty interesting concept. So, here is the same superjunction MOSFET 200 volt that we discussed, and you can see the simulated IV characteristics, and you can see that these devices have lot of carrier multiplication going on before the device actually breaks down. So, this is pre-breakdown avalanche multiplication, and this is caused by uniform electric field in the Y direction. Remember, in planar D MOSFET, the Y field is high near the p-n junction and reduces towards the bottom of the substrate, as we showed you in that electric field versus drift layer thickness slide. But here in this structure, the electric field in the Y direction is pretty high all along. That means your avalanche is taking place not just near the surface, but everywhere in the N-type drift region. So, that is why you see lot of avalanche multiplication current. So, this is a little drawback of the superjunction MOSFET. You get lot of avalanche currents flowing in the device. However, you can get much lower on resistance because we are able to dope the N-type drift layer very heavily. The other thing that we worry about is various capacitances. The most important capacitance we worried about is the gate drain capacitance, because that determines the switching speed of this device. So now you can imagine that at low drain voltages, this n-type drift layer will be fully depleted, which means gate drain capacitance, which is the capacitance between gate and the drain terminal right here, that will reduce very quickly and will go to 0 when n-type drift layer is fully depleted at low drain voltages. And that is shown here. You can see that the reverse capacitance, which is CGD for the 200 MOSFET structure, because where the P pillar was 3 micron, the P pillar was 1.5 micron, N pillar was 1.5 micron, total pitch was 3 micron, but we were only showing you half the structure. The dopings were 2 times 10 to the 16, and you can see that the CGD very quickly goes to 0 at around 18 volts. And that's when at 18 volts we have completely depleted both N and P type regions. So this is an advantage of this structure. You can see that CGD quickly goes to 0. That means this device will have a much higher speed, switching speed. The same structure can be made with trench MOSFET, which is the topic of the next lecture, but here you can see the P type and the N type pillars in this device. This is the 6th generation of CoolMOS available from Infineon Technologies, and you can see how we make this P and N pillar. We implant P type region and grow the N type layer, then we implant P again, grow the N type again, and we can do this about 5 or 6 times or 7 times. After that it becomes really expensive, and maybe the quality is not as good for the subsequent epi layers. But nevertheless, these devices are commercial and they work very well. So one technique is to implant, grow, implant, grow, implant, grow for many times. The other technique is shown here. This is a paper presented by authors from Denso in 2008 at ISPSD, and you can see that in this case what they are doing is growing the whole N-type drift layer and etching the trenches, and then growing inside the trenches a P-type layer. So this is another way of making these devices, which is much cheaper, because you can etch a big trench and then fill it with P-type semiconductor, and again the structure would be alternate P and N-type pillars. So this structure is very popular in silicon. In silicon carbide we still have not been able to make it. So in silicon, essentially, if we were doing a planar DMOSFET structure, we will probably stop at 400-500 volts. But since we can do super junction structure, which has a much lower R on, because we can dope the N-type pillars very heavily, then we can now make these devices up to 900 volt. Again, in silicon carbide we haven't figured out how to make them. The implant regrowth becomes very difficult in silicon carbide, but perhaps etching the trenches and filling the trenches by epitaxial growth is a way to go. Several research groups are currently working on it. So with that, I would like to stop here, and we will talk about the trench MOSFETs in the next lecture. Thank you very much.